number 1. The given for this problem for the compressed air, 25 degrees Celsius and 5 bar, chilled air, 25 degrees Celsius and 1 bar, and for the warm air, 75 degrees Celsius and 1 bar, and a CP of 7 halves are. Assumptions: it is an adiabatic operation, negligible changes in KE and PE, and there is no shaft work. Required is the ratio of chilled air to warm air the device produces and determine if process is consistent with second law. Solution: for our energy balance, applying our assumptions, we are left with N delta H is equals to 0, where N delta H is the N of chilled air times the delta H of chilled air plus N of warm air times the delta H of warm air, where delta H is equals to Cp delta T. Then by using our temperatures, we can get that the ratio of the chilled air to the warm air produced by the device is 1. For a 1 mole basis, we can get that the N of chilled air is equals to 0.5 moles and the N of warm air is equals to 0.5 moles. Thus, the second law states that the delta S is greater than or equal to 0, where delta S total is equals to NCPln T2 over T1 minus RLn P2 over P1. By substituting our values, we can get that the value of the delta S total is equals to 12.97 joules per Kelvin, which satisfies the second law statement that delta S is greater than or equal to 0. Question number 2. The given for this problem, at the initial state, the steam is at 6 megapascals, 400 degrees Celsius, and the Q of 95 kilojoules per kilogram. The tank is at 0.4 cubic meters, and the temperature of the surrounding is 25 degrees Celsius. At the final state, the tank is filled at 6 megapascals. The required for this problem is the final temperature of the steam in the tank immediately after the valve is closed, the entropy change of the universe, and the lost work during this process. With our energy balance, we can get that U2 is equals to H prime plus Q, and from the table F.2 superheated steam, H prime at 6 megapascals and 400 degrees Celsius is equals to 3180.1 kilojoules per kilogram. By using our values for U2, we can get the value of 3185.1 kilojoules per kilogram. And by using this for solving for T2 by interpolation, we can get that T2 is equals to 501.47 degrees Celsius. To get the value of mass, we need first to get the value of specific volume at 6 megapascals and 501.47 degrees Celsius. And by interpolation from 500 degrees Celsius to 525 degrees Celsius, we can get the value of V2 of 56.72 cubic centimeters per gram. And by converting it into cubic meters and multiplying it to the volume of the tank, we can get the mass of 7.053 kilograms. From our entropy balance, we can get that the entropy gained is equals to entropy at 400 degrees Celsius plus entropy at 501.47 degrees Celsius minus the heat transfer to the system over temperature of the surroundings. From table F.2 superheated steam at 6 megapascals, the entropy at 400 degrees Celsius is equals to 6.5462 kilojoules per kilogram Kelvin, and by interpolation at 501.47 degrees Celsius, the entropy is at 6.8862 kilojoules per kilogram Kelvin. By substituting our values and multiplying it to the mass of 7.052 kilograms, we can get that the entropy change of the universe is 4.6447 kilojoules per Kelvin. To calculate for the lost work, we simply multiply the temperature of the surroundings to the entropy change, which is 298.15 Kelvin times 4.6447 kilojoules per Kelvin is equals to 1384.82 kilojoules of lost work.
For problem number 3, we are given a shell and tube heat exchanger, which is an example is shown below. designed to warm air from the environment by condensing steam given as water that is passed through the tubes on the other side, on this side. The maximum airflow is 30 kilograms per minute, and the air is inlet at the temperature and pressure of 285 Kelvin and 1 bar respectively. The steam flows through the system at a pressure of 10 bar and a flow rate of 3 kilograms per minute. The quality of the steam at the inlet is 0.9 and the exit is 0.2. So the list of unknown would then be the final temperature of the air stream, the change of entropy of each stream, the air and water, and the lost work, which is what is required. For our solution, we start with what is required, which is the lost work, given by the equation negative TO times the change of entropy of generation, which is shown by equation 5.43, in which TO is just the surroundings temperature given by the value 285 Kelvin. To find the change of entropy of generation, we use the entropy balance, which is equal to the rate of change in entropy of the flowing streams plus the time rate of change of entropy of the control volume plus the time rate of change of the total entropy of the surroundings. We know that there is no rate of change in entropy of the flowing streams since there is no change of temperature, as well as there is no time rate of change of entropy in the control volume for the same reason. Therefore, the change of entropy of generation is just equal to the change of entropy of the surroundings. Now we find an expression for the change of entropy of the surroundings, and we know that it is equal to the change of entropy of the air plus the change of entropy of the steam or the water. The change of entropy of air is just equal to the entropy at the outlet rather, minus the inlet, which is the same for the change of entropy of steam, which is just equal to the entropy of the outlet minus entropy of the inlet, shown as S4 and S3. We use molar flow rate for air since CP calculations has units kJ per mole. We use mass flow rate for H2O since steam tables has units kilojoules per kilogram. Now we find the molar flow rate for air, which is just equal to the mass flow rate of air divided by its molecular weight, which is 0.029 kilograms per mole, which gives us the value of molar flow rate of air to be 1034 moles per minute. Next, we find S2 minus S1 by using equation 5.14 of our textbook, which is shown on this expression. We multiply both sides by R. Then we know that P equals PO given a value of 1 bar. And we know that ln1 is just equal to 0, which cancels out this expression. Therefore, the change of entropy S2 minus S1 is just equal to this expression, which is the integration of Cp over T dt. Now we find an expression for Cp of air in terms of T, which we could use the expression used in table C.1 given on this expression, in which the values of A, B, and C are shown. Now we plug in the expression for Cp of air to S2 minus S1, which gives us this integration form. Then by integration, we are given by the final expression for S2 minus S1. However, we can't solve for S2 minus S1 directly since we don't have T2. Next, we get S3, the specific enthalpy of 0.3 and specific enthalpy for 0.4 by using the definition of quality. The definition of quality is given by this expression, in which the quality for zero point 0.4 is just 0.2 and the quality for 0.3 is just 0.9. Next, we find the specific entropy of the saturated vapor and the specific entropy of the saturated liquid by using table F of our textbook, shown as steam table. By plugging in the values, we get that the specific entropy of 0.4 is just equal to 3.028 kilojoules per kilogram Kelvin, while the specific entropy of 0.3 is just equal to 6.142 kilojoules per kilogram Kelvin. Since we can't solve S2 minus S1 because T2 is unknown, we could use energy balance to find T2. Our assumption then would be that there would be negligible shaft work, no kinetic and potential energy. Also, there would be no heat loss outside our control volume. Then, our energy balance would then become that the change of enthalpy of air is just equal to the negative change of enthalpy of the steam. Therefore, it would be this form. So we know that the change of enthalpy of air and the change of enthalpy of steam is just equal to the difference of their outlet and inlet, shown as H2 minus H1 and H4 minus H3. To get H2 minus H1, we use the expression, the integration of Cp of air dt from T2 to T1. From T1 to T2 rather. Then we use the same expression for Cp air from S2 minus S1, this to give us this expression. Then by integration, we get this expression labeled as 0.2. Similarly, the previous expression for the energy balance is labeled as 1. By using the same definition of quality, we substitute the specific enthalpy of saturated vapor and the specific enthalpy of the liquid by using the table F, steam table, then substituting the values to get the specific enthalpy of 0.3 and specific enthalpy of 0.4 to be 2576.6 kilojoules per kilogram and 1165.9 kilojoules per kilogram respectively, which is labeled as 3 and 4 respectively as well. Now we substitute 2, 3, and 4 into equation 1, which is our energy balance. Then using Goal-Seek in Excel or any mathematical computational software gives us the value of T2 to be 423.8 Kelvin. Now we found T2. Then we substitute this value to find S2 and S1. So, from our derived expression of S2 and S1, we substitute the value of T2 and T1 to give us a value of 11.7 joules per mole Kelvin. Now we find the change of entropy of generation by substituting S2 and S1, S3, and S4 to the change of S or the entropy of surroundings given by the expression. Then it gives us a value of 2755.8 joules per minute Kelvin, which therefore is equal to the change of entropy of generation. Now we can compute for the loss work, W lost, which is equal to the temperature of the surroundings times the change of entropy of generation. By substituting the values, we could get the value of the loss work to be 13.09 kilowatts.
For problem number 4, we are given a problem in which we consider a piston cylinder assembly containing an ideal gas that undergoes a reversible expansion process. From the problem, initial and final pressure, initial temperature, and initial volume were given along with the ambient pressure and temperature. Mean heat capacity and the pressure-volume relationship is given as well. We are asked to calculate for the work obtained in the process, the useful work, exergy and ideal work, and the lost work. Before solving for the required, we solve first for the number of moles in the cylinder using the ideal gas equation. V2, on the other hand, can be calculated through the use of the pressure-volume relationship. Since work is equal to the negative integral of PdV and P is equal to the given expression, we can now solve for the work obtained in the process, which is equal to negative 4042.22 joules. Moreover, useful work can be obtained by subtracting the work obtained in the process to PdV. We calculate first for the volume at the dead state, which is equal to 9.38 times 10 to the negative 3 cubic meters. Since we have the volume at the dead state, we can now solve for the useful work, which is equal to negative 3,264.19 joules. Ideal work is the negative value of exergy. To get ideal work, we use the formula change in enthalpy minus ambient temperature multiplied to the entropy change. To calculate for the ideal work, we must calculate T2 first by the ideal gas equation, which is equal to 368.423 Kelvin. Now that we have our T2, we can now calculate the ideal work, which is equal to negative 3,795.02 joules. Going back to what I mentioned earlier, wherein ideal work is the negative value of exergy, we then have exergy equal to 3,795.02 joules. Lastly, to calculate for the lost work, we get the difference between the actual work of the process and the ideal work for the process. We get work loss equivalent to 247.200909 joules.